Hello everyone, welcome to chapter 15, Kinetics of a Particle, Impulse and Momentum. This module is going to discuss impact in oblique impact cases. The objectives are similar to the previous module. We want to understand and analyze the mechanics of impact, but in this case we want to analyze the motion of bodies undergoing a collision in oblique impact cases. So this case of central impact was done in the previous module. Now we are going to go for oblique impact. Just as a summary, things that we have mentioned before in the previous module, impact usually occurs when two bodies or two particles collide during a very short period of time, causing large impulsive forces to be exerted between the two objects. One thing that we need to define, which is the line of impact. To refresh your memory, this is the line that connects the center of masses for both particles. So based on the definition of the line of impact, we are going to differentiate between central impact, which we did last time, and oblique impact, which we are going to discuss in this module. Now, when you connect the center of mass of the two particles, okay, so this is my line of impact. If the two velocities, and it has to be both of them, if both velocities of the particles are acting in the same line of impact, then this is called central impact. If at least one of them, and again this is very important, if at least one of them only has a velocity, as you can see in the figure below, that is not acting in the same line of impact, then this is called oblique impact. Now, we need to define or give a name to the line that is perpendicular to the line of impact, which in this case we call it plane of contact. And keep the name in your mind because we are going to use this terminology. So, in an oblique impact, one or both of the particles' motion is at an angle to the line of impact. Typically, there will be four unknowns. Why? Because VA in this case is coming at this angle, so after it hits B, I'm expecting it to go with something like this. And B is going to reflect with something like this. Now, the two unknowns are basically going to be VAX2 and VAY2. And also here I'm going to have VBX2 and VBY2. So I have four unknowns, as you can see. And for these four unknowns, I'm going to need four equations to solve it. So let's look at the diagrams for the impulse and momentum. So for block A, the initial velocity will have two components, one in X, one in Y. And then I have the impulse coming from B on A. Okay. And then finally, I have the two components that we just discussed, VA2 and VX2. These are the linear momentums. And the same thing for B. So I have A and I have B. Now let's look at the X-axis. In A, I have linear momentums acting in X-axis, and I have an impulsive force F. Let's look at particle B in the X-axis. I also have linear momentums, mb vbx1, mb vbx2, and I also have an impulse momentum of F acting in the opposite direction. If I consider A and B together along the X-axis, the two impulsive forces, integration of F dt, will cancel because they are in the opposite direction. And I end up with conservation of momentum along the line of impact. This is similar to the central impact case. I can also, since it is similar to central impact, apply the coefficient of restitution. Now, these are two equations, but I have four unknowns, so I have two extra unknowns. Let's look at A separately, A alone. Initially, along the contact plane, I have MA, VA, Y1. And then I have no forces. You can see no forces acting in the Y direction. And then finally, I have MAVAY2. Therefore, if I take A and A alone, I can do conservation of momentum along the y-axis. This is my third equation. Also, I can do the same thing for B. I have MBVBY1, no forces in the y direction, and I have MBVBY2. Therefore, the fourth equation is also conservation of momentum along the y-axis for the B particle alone. So as a summary, just to go through the analysis procedure, and I highly recommend that you follow this procedure when you solve problems to avoid doing any mistakes or steps that you might miss if you do not follow this procedure. First thing, and this is very important, and many students skip these steps although they are the essential steps to solve these problems. First, establish the x-axis along the line of impact. Connect the center of masses, and then call this line your x-axis is your line of impact. Then the line perpendicular to it is going to be your contact plane. After this, resolve the velocities in their x and y components, as we just did in the discussion in the previous slide. So you can do these four components. The same thing for the initial velocities, by the way. And then after this, you can apply conservation of momentum along the line of impact, apply coefficient of restitution again along the line of impact. So these two equations will solve your x unknowns, which is VAX2 and VBX2. After this, you apply conservation of momentum along the contact plane for A alone, and then apply the same thing for B alone. This will give you the y components, and then you end up solving all the unknowns in this problem. So let's start with the first example. A 0.5 kilogram ball is ejected from the tube at A, as shown in the figure, with a horizontal velocity of 2 meters per second. The coefficient of restitution at point B is given as 0.6. Find the horizontal distance r, as shown in the figure, where the ball will strike the smooth inclined plane. And then find the speed at which it bounces from the plane. After it leaves the plane, found that speed. So, first of all, let's find this horizontal distance r. Basically, you have a ball that is being ejected, and as you can see that it follows a projectile type of motion. Therefore, this first part of the problem can be solved using projectile motion. So, the plan is that first we are going to use kinematics to find the distance r using projectile motion. Now, after this, the ball is going to hit the ground and then it will bounce back again. So this is an oblique type of impact. Then I'm going to apply the equations of oblique impact and coefficient of restitution, with all equations that we need. Okay. So therefore, we start with the projectile type of motion. I'm going to pick the origin for my case, let's say at point A. So here is my x and y. These are my origins. So let's start. First, I'm going to apply the equations of projectile motion to determine r. First, I'm going to take everything from the x-axis. So now let's start from point A. I'm going to do the x-axis. I have an equation that says x should equal to x0 plus Vx0t. Okay, and this will give me final xr should equal to 0 initial location plus initial velocity was 2, so it's going to be 2 multiplied by time. Okay. Second equation, I can do it from the y-axis. I'm going to say y should equal to y0 plus v0yt minus half gt square. and this is giving me, now the y-axis is going to be below my reference in here, so it's going to be minus 4, and then you're also having r, and then you can say r tan 30 to write everything in terms of r, because if you are going to use this value here, let's call this rx and this is ry. If you're going to say 4 plus ry in the minus direction, ry is going to be an additional unknown. So I want to write things in terms of rx. So I'm going to say rx tan 30, because tan 30 is going to give me ry over rx. This is the tan. If you multiply by rx, you end up with ry. So I can write it in terms of only rx. So it's going to be minus 4 plus tan rx. Let's call this rx. Okay. Sorry, it should be rx tan 30. My mistake. So it's going to be 4, okay, plus rx tan 30, okay. Now, this should equal to 0, original location, plus initial velocity in the y-axis was also 0, and then I end up with only the gravitational part, which is half gt squared, and g equals to 9.81. Solving those two equations, let's call this 1, this is 2, so solving 1 and 2 leads that t should equal to 1.028 seconds, okay, and r, we already can find it from here, 0.28 seconds, and then r, which is what is asked in the problem, equals 2.06 meters. Okay. Now, I need to find the velocity after the ball leaves the ground, after it bounces. Now, we know from projectile motion that the initial horizontal component of the velocity, Vx, does not change. So it will remain. So when the ball hits, just before it hits the ground, so this velocity, okay, so just before the ball hits the ground, okay, it's coming with this velocity at this angle. The x component is known. I only need to find what is the y component of that velocity. So therefore, I can also calculate this. So Vx, when it hits the ground, it's going to be Vx0, which equals to 2 meters per second. Does not change. This is horizontal to the right direction. And then I can solve from the projectile motion for Vy, should equal to Vy0, okay, minus gt, and this should equal to initial velocity is 0 minus 9.81 multiplied by the time, which is 1.028, and this should equal to minus 10.0886 meters per second downward. Now I have the two components. I can find the magnitude at and angle. So V should equal to square root Vx squared plus Vy squared, and this will give me that the magnitude of the velocity equals to 10.285 meters per second. And from the y and x components, I can find the angle as tan inverse y over x. So we can say theta equals to make sure that there's no theta used in this problem. So theta equals to tan inverse of Vy of Vx, and this will give me 78.8 degrees with the horizontal. Okay. with the horizontal. So now I found the velocity and r values. Now the problem says find the horizontal distance r. We've done this, where the ball strikes the smooth inclined plane, and the speed at which it bounces from the plane. So now I need to perform the oblique impact analysis. So first of all, let's draw the problem so that I know what kind of impact and how does it look. So I have something like this. This angle is given to me as 30 degrees. This is the ball as it hits the line. Now, whenever you have problems where you have an object that hits the ground, the line of impact, basically, it's like connecting the center of this to the center of Earth. So it's going to be along this line. So this is my x-axis. This is my line of impact. And perpendicular to it here, okay, this is my y-axis. Let me take it to the other side just so that it won't take much space. So it's going to be, let's say this is my y-axis. Okay. Now, the initial velocity, as you remember that we just solved it from the previous problem of the projectile motion. This is the initial velocity, and it was coming at an angle of 78.8 with the horizontal, with this line. But this angle is 30, therefore this velocity is directed with an angle of 48.8 with my y-axis. Because 48.8 plus 30 will give you the 78.8. So this is VA1. And VA2 is unknown, so I'm just going to assume something. So it's going to be VA2, something like this. So now let's apply conservation of momentum along the y-axis. So this is going, I have no forces acting in the y-axis, so I can do it directly for VA. It's going to be simple. So I'm going to do VA1y should equal to VA2y. And this basically gives me that MA multiplied by minus VAY1, because it is acting in the opposite direction, should equal to MA times, again, minus VAY2, because it's to the right side in this case. So the mass will cancel, and I end up only with the velocities. As I said here, that you're going to have, sorry, this was MV equals MV. So now if I apply this, it's going to say that MAY2, which I need to find, should equal to MAY1, which equals to VA cosine 48.8, which equals to 6.77 meters per second. The two are the same, so magnitude and cosine 48.8 should equal this. Now, do not make the mistake of using this velocity saying Vy is the same. The y defined for my projectile motion is different than the y defined for my oblique. I no longer use that terminology. I'm using this definition right now. So this is the new velocity in the y-axis. Now, I need to apply the coefficient of restitution. Now, one mistake that also students do, and this is something that is not straightforward, whenever you have an impact problem like this, so the velocity of Earth, you don't know it, and in this case we consider it to be zero. It's relatively zero compared with the motion of the particle. So you only have one unknown in the x-axis, which is the velocity of the particle and not Earth. In this case, do not use conservation of momentum, but use the coefficient of restitution. You cannot use conservation of momentum because we do not have two particles with two velocities. I only have one particle hitting the ground and changing velocity. Did it change the velocity because A was moving and there was a change in energy? No, because the Earth was not moving. Sorry, but the velocity of A will change because of the coefficient of restitution. Therefore, again, do not say MA VA1x should equal to MA VA2x. This is wrong. Only use the coefficient of restitution. So I'm going to say E equals to, if we consider the Earth as B, so we're going to say VBx2 minus VAx2 over VAx1 minus VBx1, and apply the values that we have. This coefficient was given as 0.6, should equal to, Earth, as we said, is relatively not moving, so it is 0, relatively small, minus. Now, let's look at our assumption. VA, we are assuming it's going at this angle, so the horizontal component, no, sorry, the X component, not the horizontal, the X component is going in the positive direction. So it's going to be minus, which is part of the equation itself, has nothing to do with the direction, minus, and then VA is going to be the same, VAx2, positive, over VAx1 was coming with a component that is opposite to my positive X, so it's going to be negative. So it's going to be minus 10.285 sine 48.8, okay, minus initial velocity of Earth is the ground is also 0. Solving this gives me my unknown that VAx2 should equal to 4.64 meters per second. Now I have the two velocities. The problem asks you to find the speed. Speed is a scalar quantity. That means speed is the magnitude. So speed of A, VA2, should equal to square root of VAx2 plus VBx2. And this should give you a value of 8.21 meters per second. And this solves this example to you. This is a good example, although this is not a traditional oblique impact problem, but it's good to show you that when you have an object hitting the ground, do not use conservation of momentum along the line of impact. Pay careful attention to my terminology. You do not use conservation of momentum along the line of impact, but you use the coefficient of restitution. Now, the second example is a traditional oblique impact problem. So disks A and B have a mass of 6 and 4 kilograms respectively. If they are sliding on the smooth horizontal plane, smooth, there's no friction, with the velocities shown. So these are the initial velocities that are given in the problem. Determine their speeds just after impact. And the coefficient of restitution between the disks is given as 0.6. So the first thing we need to do is that to draw a free body diagram to show all the velocities and the forces acting on it. So I have block A and block B. So block A is bigger, disk A and disk B. So this is roughly disk A. This is disk B, as we have in the problem. Let me connect the centers of masses. So this line, the center of mass, this is basically my line of impact, okay? And I'm going to call this my X. This is my line of impact. And if you remember, perpendicular to it, we have the plane of contact, and this is going to be my Y, okay? Now, initial velocities that are given, I have for block A, it was 10 meters at 45 angles, at a 45 angle. So it's something like this. So this is 45, and this is 10 meters per second. And this is block A. Now for disk A. Now for disk B, velocity was 5 meters with 30 degrees with the horizontal. So 30 degrees again with the horizontal, not with the line of impact. So it's coming something like this, and it has a value of 5 meters per second. So 5 meters per second, and the angle here is 30 degrees with the horizontal, and this is not with the let me fix the angles just quickly. So okay, so in this case I'm gonna fix the angles. Let me draw the horizontal line. So this is a horizontal line. Sorry, just let me fix it. So again, so this angle was given 45 with the horizontal, and this is 30 with the horizontal. So I'm gonna draw these with the horizontal. So this angle is 45 and this angle is 30 degrees. Okay, now as you can see, these are the two. Now what I need to do is look at the final velocities. I have to assume a certain velocity when they leave. So after they leave, A might have like a velocity like this, VA2, and B might have a velocity something like this, VB2. Okay, so now I have 4 unknowns, 2 components for VA2 and 2 components for VB2. Okay, so looking at the problem now from this point of view, let me start now writing the conservation of momentum. I'm going to take, this is my positive x-axis, so we'll start with conservation of momentum, and this is the positive x. I have MA VAX1 plus MB VBX1 should equal to MA VAX2 plus MB VBX2. Write all the terms, just open them. Sorry, this is Y, X, sorry, yes. So just write the all the terms together. Do not start substituting any values, just write them so that you know what do you have. Now let's start with the first one. With the x-axis, I need to find what is the angle between this velocity and my x-axis. So I need to find this angle between them. In the problem, it was given that the angle between the horizontal line and the line of impact is 30, as you can see. Therefore, if you open this one, this angle is 30. Okay, so 30 with 45, you end up with 75 between the 10 and the x-axis in our problem. So this is going to be, this part is 30, and you add the two angles together. So is it going to be plus or minus? The x component of this is going to be in the minus x-axis. So I have minus the mass, which is 6, okay, was given to me as 6, and the other one as 4. So minus 6 multiplied by the velocity, which is 10 cosine 75 degrees. Now for VBX, you can see that initially the component of this is the original velocity for A, it should be positive, and B, initial velocity should be negative. So I'll correct this one. So this is plus 6 times 10 cosine 75 minus the mass of B, which is 4, multiplied by the velocity, which is 5 cosine 60. This should equal you can just for the sake of solving things in a different way, instead of saying components in x and y, I'll show you how to solve the problem with angles and magnitudes. So instead of saying VA x2, I'm going to write it as minus the mass, which is 6, multiplied by the magnitude VA, okay, cosine an unknown angle. So I'm going to say this angle, I'm going to call it phi A. And this unknown angle, I'm going to call it phi B. So I don't know these angles. I'm going to solve them as unknown. So it's going to be VA cosine phi A. And then you have plus the mass 4 times VB cosine phi B. So I have 4 unknowns, VA, VB, and cosine phi A, cosine phi B. So just rearranging all of this gives you that 4 VA cosine phi A minus 6 VB cosine phi B should equal to 5.529. And this is our first equation. Now, my second equation I can do in this case is the coefficient of restitution along the same positive x. So we're going to say E should equal to VBx2 minus VAx2 over VAx1 minus VBx1. Okay, and this gives me 0.6, which is given in the problem, equals to, now let's look at VBx2. Is it positive or negative? VBx2 has a component that is positive, so I'm going to write it as VB cosine phi B. Okay, and minus, which is part of the equation, let's look at VAx2. The component of the final velocity in the x-axis is negative. This is my positive x direction, so it's going to be negative. Therefore, it's going to be minus VA cosine phi A over, now you switch both of them. Initially, VA was positive, so it's going to be over 10 cosine 75 degrees, and then you have minus, okay, and by the way, VA was minus, so it was VA was minus, so this is going to be plus, and I have 10 cosine 75 minus. Let's look at the initial velocity of B in the x-axis. It was negative, as you can see, compared to this one. So it's going to have minus. Also, you have minus. So it's going to be minus 5 cosine 60. Okay. So there you have. So these two minuses will cancel. So it's going to be positive. And VAx1, as you can see, it was coming at a positive value. Okay. Now, VAx2 is negative. So I can put the value here as negative. Therefore, I have this as positive. Okay. So this will give me an equation that is as follows: VA cosine phi A plus VB cosine phi B should equal to 3.053. And this is my second equation. Now, the third equation, which basically will be the conservation of momentum in the y-axis for each particle. So let's start with disk A, and you can see here that our positive y-axis is acting upward. So upward is positive. I'm going to say MA VA Y1 should equal to MA VA Y2. Now this is basically MA VA1. If you look at the direction, initially this gives me a positive component in the y-axis. So it's going to be plus. So it's going to be the mass, which is 6, times the velocity, which is 10. And the component is sine 75. Because this angle from here to here is 75, and you need the y component, so you take the sine of that angle. Okay, so 6, the mass, times 10, the velocity, sine 75, should equal to, the final velocity is also positive in the y-axis, going to be 6 VA sine phi A. Therefore, VA sine phi A should equal to 9.659. This is the third equation. And for B, I can do the same thing. MB VBY1 should equal to MB VBY2. And for VB, both initial and final velocities both are in the negative y component. So this will give me minus 4, which is the mass, 5, which is the velocity, and the angle is 60. So sine 60 should equal to minus 4 times VB sine phi B. And this will give me that VB sine phi B should equal to 4.33. And this is my fourth equation. Now I have 4 equations with 4 unknowns. If you solve all these 4 equations simultaneously using a calculator or by hand, you get that the magnitude of the final velocity of A equals to 9.68 meters per second with an angle phi A equals to 86.04 degrees. And final velocity for B should equal to 4.94 meters per second, and also I can find the angle of phi B equals to 61.16 degrees. Now, I would recommend that you repeat this problem, but instead of using these 4 unknowns, solve it for VAX2, VBX2, VAY2 and VBY2, just to get a different feeling of how to deal with these unknowns and how to solve the problem. With this, I conclude the modules for central and oblique impact. I hope that this was useful to you, and I wish you the best of luck in your future studies. Thank you.